That's nice.
Is that okay? Fine for me. Okay for everyone else? All right, I guess, is this thing? Not sure how this.
I don't know.
I didn't want to stand behind the podium. I heard that's like a bad thing to do. So, all right. Well, all right. My name is Jeff Mose. I am a software developer and math enthusiast. So no hard questions. Actually, you can ask me anything. It's kind of a joke. So anyway, a while back I thought it would be cool to do a talk on graph theory since Neo4J is related to graph theory, and so I figured it would be kind of cool to do a talk. So I thought of like how could I do this and how could I relate it to Neo. This talk is going to be a fair amount of math. But it's the nice thing about graph theory is it's very visual, and hopefully I have lots of pictures that make the concepts seem at least somewhat understandable. And I wanted to look at the other thing too about graphs is that how do they work and sort of like kind of have an overview of the structure. I guess to look at the I guess what you call the language and the structure and patterns that you find in graphs. And then, what I like to call it is that, with things like Neo, you're sort of relating a lot of different things that are kind of unstructured. But really, when you're dealing with graphs, there's actually structures in your data, in the graphs. And so, from the graph theoretic mathematical standpoint, so it's sort of the, what is the structure of this unstructured data that we're looking at. And the goal of this talk, there's going to be a lot of concepts here, so the goal of this talk is to kind of walk you through, it's kind of a survey of these ideas. Don't expect to like walk out of the room and like know all these cold, because it takes time to learn all this stuff. But hopefully and I'm going to make these slides available, so hopefully if you're interested, you can follow through on things and look things up. And there's tons of resources out there. I list a few, but just this day and age now, there's just so many resources on mathematical topics and academic topics. It's amazing. Too much stuff to actually read and learn. And this talk is really the tip of the iceberg of graph theory. There's all these areas sort of lead into all these other areas in graph theory. So if you get interested in it, you could pick like one of these individual topics and probably spend your whole life exploring it. And I've got lots of pictures, so hopefully that will help. And then I guess the question is why learn it? We really are living in this connected world. So it's it's increasingly connected. We're building more and more data that's connected. We're discovering more connections, and the other nice thing about graph theory is it's very intuitive, and its ubiquity makes it very natural. And the one thing I like to say is that you probably never learned it in school, so the educational system didn't ruin it for you. It's I like to call it the gateway drug for maths, because it connects to so many other areas of math, and it's also extremely central to computer science. So I want to do a brief history. Actually, one of the things about graph theory I think is really interesting is how new the field is, and so this is sort of the obligatory Euler problem of the 7 bridges of Königsberg, where he was working for the Russian, I think one of the Russian czars, and he was living in Königsberg, and there was a common thing in the town where you'd be like, well, can you walk across these 7 bridges once and end up where you originally started? And this over here is actually what the graph looks like, and what he recognizes this as a geometric problem where distance didn't matter. It was really about how things were connected. And this really is sort of considered the watershed moment for the development of graph theory and topology. And topology is sort of a broader area. Sometimes I've seen one lecturer refer to it as rubber sheet geometry. We'll talk a little bit about that, but it's a whole branch of math in and of itself. And then it seemed like not a lot. That was in 1736, and it seems like not a lot really happened until maybe the early 1800s. And then you had in the 19th century, you had a number of things that had happened. Mainly these events like Kirchhoff and electric circuits, Hamilton with the Hamiltonian cycles, and then Cayley and several others looked at chemical molecules in terms of graphs. And this is actually found kind of interesting, is a guy named Francis Guthrie, who I think was a student of Augustus de Morgan, who's known for the logic laws, De Morgan's theorem. Actually, I guess, introduced De Morgan to the four-color problem. And the four-color problem actually seemed to dominate graph theory for probably about 70 years, from the 1852 to the maybe around the 1920s. It was actually the dominant part of graph theory. And we'll look a little bit at that as well. And I've kind of found this sort of a cheesy infographic here to show like exponential growth. But graph theory really took off in the 20th century. And well, Kuratowski's very famous, and we'll look at his theorem. And there's a guy named Tut, who's something called a Tut polynomial, which we're not really going to look at. And there's a very famous mathematician, Erdős, and Renyi did a lot of work on random graphs. And that work is actually becoming very important in terms of things like social networking and just probability on graphs and things like that. And I looked at a couple others. I took some of these names from some lecture notes. Strogat's a fairly well-known mathematician. He did a paper on what's known, I think it's called the small world problem, again dealing with sort of social networking type, random type of topics. And so anyway, I really find it fascinating, because really everything that's happened in graph theory that's sort of relevant to like all the stuff that's happening right now, it's sort of happened in maybe even the last 50 years. So it makes it a really young field. And I find it rather exciting and rather interesting. So I guess the question is, what are graphs? I mean, if you think about graphs, well, so what they are is they're essentially points and lines, and you're not really concerned with the geometric distance. So essentially, your metro, the classic example is your subway maps. I think all the Neo guys use the London Tube, but I figured since we're here in DC, I'd use the Metro. And this kind of shows, and the interesting thing is these maps are very intuitive to people, but if you look at them, you can see, like, if you get on at Vienna and go to Roslin, that distance on this map is actually about the same as Roslin to Metro Center. And if you know the area, you know that it's definitely not the case. But it doesn't prohibit people from looking at the map and being able to find their way around the metro. So it is this sort of natural, intuitive concept. And then this graph, this is what's called the Peterson graph. We'll see a little bit more about this later. And this is 4 different drawings of it. And from the graph theoretic, mathematical perspective, this is the exact same graph. So it's just drawn in different ways, but it doesn't matter. It's from a graph theory standpoint, it's the same exact thing. One concept of graph theory is that basically 2 vertices are considered adjacent if they have an edge connecting them. So that's sort of a basic concept. And then really the thing is the graphs are really about relationships, and that actually is probably kind of the Neo. One of the things about Neo is that you're really talking about your data and how things relate, or modeling the real world, or abstract ideas. So I thought it'd be fun to just sort of list out a few graphs in various areas, sort of the STEM disciplines, because sort of the typical examples of graph are the social networking, or family trees or stuff like that. So I just threw together a few things, and these are just a couple. These 2 things are lattices, and I'll just go through these real quick because I don't want to bore you guys. But and then you have things in math called Cayley diagrams, which are actually these 2 guys are actually group theory related things. This is both what's called a dihedral group, and this is sort of a lattice of subgroups, and this shows how the elements of that group interrelate. Game theory has these decision trees that show you outcomes. This is Markov models, which really are random walks on graphs. And then category theory has these commutative diagrams, again, are graphs. So you actually have graphs appearing in math that you use in other areas of math. And then computer science is really rich with graphs. You got finite state automata, you got data structures, like red-black trees, or skip lists, and linked lists, or really anything you can think of. And then formal language theory and natural language and computational linguistics, you've got parse trees or derivation trees, linguistic semantics, semantic nets or ontologies, and then neural nets, of course, are a big thing now too. And then physics has a few. There's the particle interactions, Feynman diagrams, and this is actually a stellar fusion process. And I think it's interesting because these processes, and we'll see some in biology as well, have these sort of graph-like structures. Chemistry molecules. There's actually a whole discipline called chemical graph theory. And so that actually gets into applying graph theory to chemical molecules. This is actually a metabolic cycle here. It's kind of interesting because the process itself is a graph, and it's actually, you have these molecules which are sort of changing. So you've got these sort of graphs transmuting through this process. Biology, you've got, again, a lot of processes. This is actually a yeast life cycle, so some of us are enjoying some yeast byproducts right now. And a less, I guess, glamorous one is a malaria parasitic relationship here. And then you've got things like nitrogen cycles, how nitrogen is sort of recycled through, absorbed, and then reintegrated back into the atmosphere. And then you've got taxonomies of species. All graphs, and we'll look at the idea. Some of these have these cycle structures, and then this one doesn't. And we'll look at those ideas in more detail. Engineering, things like microprocessors and electric circuits. You have issues of planarity and crossing, which we'll look at. And then in networks, this is a refinery, and this is actually a system from the International Space Station. And these things deal with flow, and the idea of network flow is actually a graph theory, a very, very prominent graph theory problem. And computer software development is just, in my opinion, all graphs. You've got database schemas, UML diagrams, and this is the visitor pattern, object graphs, even life cycles. This is a bug life cycle for Bugzilla. So these things are all graphs. So I wanted to get into I guess I'm going to talk about a lot of graph theory related ideas, and these next few slides are, I guess if you're going to come away from anything from this talk, these are probably the most basic and interesting things to sort of give you the ability to sort of maybe have a way to think about graphs at sort of a higher level. I don't know what to call them. I call them categorization or sort of metastructural or basic structural qualities. And then just a little side note here, we'll look at some matrices, and some of these ideas actually affect how matrices are formed on graphs. And then another thing is we're only dealing with finite graphs here, so no infinite graphs. The first one is, it's called a multigraph, or also known as a quiver. And it's a fairly simple principle, is that when you have vertices in a multigraph, you can have multiple edges connecting two vertices. So in this case, you've got two, but in theory, you could have a million or whatever. So, and it's an important distinction because we'll look at simple graphs as well. And there are some things when you're thinking about graphs that you're only thinking about one edge per between any set of vertices. There's also the idea of a loop. A loop is where you have a vertex connecting to itself. It's actually mathematically referred to as a reflexive relationship. And in theory, again, this is sort of this categorization thing that you can really have these on simple graphs or multiple graphs. And then also you can also have potentially multiple loops. And these would be things that you would have to, when you're analyzing graph structures, you sort of need to be thinking about all this stuff. Another important concept is connectivity. When you say graph, I mean, it doesn't necessarily mean that all the components are connected. And these are two terms that we'll see. These are trees, or they're what are called acyclic graphs. We'll look at a little bit later. And this is called a forest, and then this is called actually a pseudo-forest. And so the idea is that you have multiple connected components, and this actually plays into. We'll look at some ideas of like subgraphs and things about how connected components are. How you can go from connected graphs to unconnected graphs. And then this is a simple graph, which means pretty much, it's also referred to as simplical, single edges between vertices, and no loops. And in this case, we're talking about undirected graphs. There's also the idea of directed graphs, and directed graphs means that you have a direction between the edges. So these two have a relationship or a path that you can travel to, whereas backwards you can't. And we'll look a little bit more on these guys. And then there's this concept called hypergraphs, which we're not going to talk about, but I just wanted to mention it. It's the idea where you actually have multiple, where an edge can have multiple vertices. It actually starts to look more like this sort of topological concept. Although I have seen these come up more and more lately, so I guess they're becoming more relevant to things. So I guess, what is Neo? If you think about it, when you're working with Neo, what are you dealing with? Well, what you're actually dealing with is you're dealing with a directed multigraph with multiple loops, or you could call it a multi-loop quiver. Cipher actually allows you to query in multiple directions. So really, Cipher creates the ability to have undirected graphs. And the classic example is the friend. Matter of fact, this diagram doesn't even show directionality here, but if you were modeling this in Neo, there'd actually be a direction on this. But Cipher would let you query that. So technically, undirected edges are not first-class stored objects in Cipher, or in Neo.
So Cipher is the query language?
Cipher is the query language for Neo, that's correct. So, that's right, Wes? Right. All right, and then so a couple of quick basic ideas. Vertices can have a property known as degree, which is really just the number of edges that are connecting to them. And then in directed graphs, you can have the idea of in degree and out degree, so you can have two different numbers on that. And then there's this thing called the handshaking lemma that comes up, and the idea is that you can only have an even number of odd degree vertices. So it's kind of related to the handshaking. So you can't have this. You can't have a dangling edge if you've got. You can't have that an odd number of odd degree vertices. So that's sort of the kind of basic structural properties. And now this is, again, I'm not really sure how to call these, but they're essentially sort of special case. There's actually probably hundreds or thousands of these special cases of graphs. If you go looking around on Wikipedia, you'll find tons of them. Actually, this is I think called. I mean, that's a dodecahedron, but it's actually I guess a polyhedral graph if you drew it right. And so we're gonna look at a bunch of these. And there's a couple here that are probably worth like I said, the previous stuff is definitely worth trying to know. And then a few of these ideas. We talked a little bit about the acyclic concept, and then there's a concept of directed acyclic graphs. So these are undirected acyclic graphs. This is, I guess, two trees, which would be a forest. This is actually, even though it looks like it has cycles, if you actually follow through, you'll see that no matter where you start, you're going to always end up somewhere where you can't go anywhere. So there's actually no cycles in this graph. And that's called a DAG. It's the short term for it is DAG, and if you do a lot of computer science related stuff, you see that come up a lot. The complete graph is actually another one that's definitely worth sort of getting to know, and it's got some interesting properties to it, sort of combinatorial number theory type properties, and we'll see how this plays into the idea of density in a little bit later. So you've got so essentially these are your complete graphs, and really what it's saying is that all the vertices are connected to all other vertices. So the idea of so this is, and the K actually is for Kuratowski. So you'll see this K notation in graphs a lot, and that was done in honor of Kuratowski, who is pretty famous in graph theory and topology. But so, for example, K4, and these things are what are known as regular graphs. So a regular graph is where all the vertices have the same degree. So all these guys are regular. This has all the vertices have 2 here. All the vertices have 3. All the vertices have 4. And actually, your graph degree, all the degrees of the complete graph are going to be n-1, because you're always, if you've got 4 vertices, you're going to be connecting to 3 others. So you're always connecting to n-1 vertices. Similarly, the number of edges actually follow this I guess is kind of a number theory. It also comes up in combinatorics. Is actually what this is saying is I'm just adding up 1 through n. And so essentially, and what they do is they form this triangular structure. So that's why they're called the triangular numbers. So every complete graph, K5 for example, has the t-1 or t4 10 number of edges. So this formula will give you the number of edges for the complete graph, it's the n-1 triangular number.
So if you never have any more edges than that?
Well, not on a simple graph. On a multi-graph, if you allow multiple edges, then it goes to infinity. But this is dealing with the idea where you only have a single edge between two vertices. But yeah, that's a good point. Another one, this is actually another good one to know, and if you're getting into graph theory to learn more about. It's called a bipartite, which means two, but there's also the idea of multipartite, and there's this idea of completeness, which is slightly different than what we just saw. But essentially in a bipartite and n-partite graph, what you have is you have a partition of the vertices where in that partition there's no connections between those edges. So you have no connections between the edges here. They only connect to the other partitions, if you will. And this is only showing two. This is a very famous graph. It's called the utility graph. It's called K33. The idea is it's water, gas, and electric. I think it was probably done before internet and telephone and stuff. But, and then you have three customers. So this is considered to be a complete graph in the sense that it's complete connections between, this guy completely connects to the other partition, as does the other one. And this is also a complete bipartite. This is K53. I just threw that in there as an example. This is called K222, which means that if you look at it, none of the opposite vertices connect to each other. So you've got three sets of vertices that don't connect to each other, but they connect to all the other sets. That's probably not the optimal drawing. I mean, if I had a better drawing that drew it more like this, it would probably be a little bit better, but I stole these off Wikipedia, so that was the best one they had. These are kind of interesting. We'll look at a little bit of things on these guys, but essentially these are, and they're also pretty simple concepts, so they're kind of nice, and they come up from time to time. You get the path graph, which is just a line with n number of vertices. Star graph, where you have one vertex and then multiple ones connected out. I guess 3 is probably the smallest, because then if you took that out, you'd have a path graph. And then wheel graphs have this structure, which is just a central hub, and then all the edges are connected in that pattern. And then cycle graphs, and then you can see they all have this notation. Sort of actually, star graphs are actually bipartite. Actually, I think I forgot to mention, but all acyclic graphs are actually bipartite. And these are acyclic graphs here. And technically that would be that you could probably draw in a bipartite way if you imagine just folding the edges back and forth. And that's kind of how it works with the acyclic graphs. And the cycles are really just sort of your polygons with vertices on the edges, or at the corners rather. We talked a little bit about the idea of regular graphs, where you have the same vertex. And regular graphs seem to come up a fair amount. I kind of had to include this just because the name is called snarks. It actually was coined by, I think it's from, now I'm forgetting his name, the guy that wrote, Lewis Carroll. And it was coined by Martin Gardner, who's a famous columnist for Scientific American. And so anyway, I had to include this, but these are like these three regular, I forget exactly what they are, but this is a snark. And actually I think the Peterson graph is also, this is the Peterson graph that we saw earlier, and that's also three regular. And there's a couple other features that it has to have connectedness and whatnot. But I had to include that. And then the polyhedral graphs are kind of interesting in the sense that there's you take a tetrahedron, and this is actually our K4 graph. So that's sort of the tetrahedral polygon graph, and this is actually a dodecahedron if you just imagine stretching. And this kind of gets in that topology idea. If you take one of the edges of the dodecahedron and just sort of stretch it out and flatten it down on a plane, you get the polyhedral graphs. And then I mentioned a little bit about random graphs. I'm not going to talk about these. We'll look at density a little bit, but there's the idea of dense graphs and sparse graphs that comes up. And there's an area called expander graphs, which we're not going to talk about, but it's a pretty big area. I've seen a lot of stuff on it, and it seems to actually have a lot of applications in computer science. And then there's many others. Graphs actually are defined in terms of set theory. If you're going to get serious about learning graph theory, you really want to learn this. I wouldn't get, but if you're just starting into it, I wouldn't necessarily get too hung up on it, because sometimes I feel it kind of can muddy up sort of learning things, but ultimately you probably need to understand this. And actually graphs can be combined under set operations, so you can take two graphs and do a union of them or an intersection. or subtract them even, which is called asymmetric difference in sets. And then just sort of a little side note is that a multigraph, which actually has multiple edges, you would actually have what's called a multi-set, or in programming terms it's referred to as a bag. I had to include a little bit of topology. Graph theory really is a subdiscipline of topology, and actually I've seen it described where math is actually you could think of math as three major areas, which would be analysis, algebra, and topology. So topology, in my opinion, is sort of tragic that topology doesn't get more, I guess, recognition, and sort of, especially in education. It's sort of one of my, well, I won't get into that, but so it's a fairly major area, and actually there's some interesting topological aspects of graphs. There's actually a whole area called topological graph theory, and that actually, we're going to look at this idea of embedding. And the first idea of embedding is actually planarity, and this is actually a pretty important and fairly common, sort of basic graph theory concept. It's the idea of, can I draw a graph in a plane without any of the edges crossing? So this guy, obviously I can. This actually is not drawn optimally, but this is the K5 graph. You cannot draw this graph in a plane, nor can you draw the utility graph in a plane. And actually, you can, if you draw a graph in a plane with the minimum number of crossings, this is the Peterson graph drawn that way, and basically the Peterson graph has what's known as a crossing number of 2, because that's the minimum way you can draw it. You can't draw it with any less crossings than 2. You can draw it with more, but you can't draw it with less. And then there's this idea of the dual graph, and this is the idea of what you do is you take essentially what you call a face here, which is an area that's broken out by the graph, and then you draw a line through each edge. So you put a vertex in each face, and then you draw a new edge through the old edges. And we'll see actually this show up a little bit later, but that's a common thing that you'll see is the idea of the dual graph. And it's kind of interesting too because the idea of duality comes up a lot in math. And then briefly, this is an interesting theorem, Kuratowski's theorem. What it's saying is, and I actually have this highlighted, this subdivision idea, which I'm not going to get into because it's just a little bit beyond the scope of what I want to talk about tonight. So if you want to learn this, it actually relates to how you can sort of restructure graphs a little bit. But essentially what it's saying is that if you get, in certain forms, if you get these two guys in your graph, either of these two guys in your graph, it can't be planar. Which kind of makes sense because those two aren't planar, but he apparently distilled it down to just these two things. And then the idea of you can actually draw a graph on a plane, which actually is essentially a sphere. And again, if you take the sort of topological idea and you punch a hole in your sphere and flatten it out, or think about a map of the world, for example. So the idea is that the planarity, and so you can embed graphs on these other structures, and these structures have actually these structures all have what are known as genus, and actually genus is a pretty simple idea. These are two-dimensional surfaces, or sometimes called two manifolds in more topological terms. But the genus idea is pretty basic. It's 0, 1, 2, 3, so you can see pretty much it's just the number of holes that you have. And then the idea is that you can, just as you can draw a graph on a plane or a sphere, you can draw it on a torus. And so some of these graphs are actually toroidal. So you can draw all these graphs right here, the Peterson graph. This is actually the K7 graph, and your utility graph K3 you can draw on a torus without crossing. And then I threw this one in here. This is a Klein genus 3 graph, and you can actually draw this on here with no crossings, and if you can visualize that, you're probably a genius. It should be up here talking. So, but it's kind of interesting, and then the idea of a genus is actually a property of graphs. That it's actually called an invariant, where a graph will have a genus. So and it's actually which surface it can be drawn on. This formula comes up a lot, and I just felt I needed to touch on actually sort of a little bit of luck here, because actually I did this before I realized we were going to be doing. Is World Cup still going on? See, it shows you how much I know about sports. So actually the idea of these polyhedra, these are actually I think what are called the Platonic solids. Actually, they're four of the five. But this formula essentially what it says is vertices minus edges plus a number of faces equals this 2 minus 2g, and so these would essentially be spherical. So that term drops off, so B equals 2. This is actually one of those formulas that comes up in graph theory and topology, and it's sort of, I don't know, I consider it to be kind of one of the seminal math formulas. There's actually a book called Euler's Gem that actually talks a lot about this, and it's actually really a good thing. If you're interested in math, it's probably a really good thing to be looking into. And graph theory books will have that.
Can you go back just a second?
Oh, sure.
It was plain what E, E, and F stood for. G is?
G is genus. So so genus 0 and genus 1 here. So
basically, it's the number of holes, right?
Basically, the number of holes. So, and the most common form of this is that you usually see is without this term because they're usually just talking about these guys. And this is actually, by the way, it's called a truncated icosahedron, I believe. So, or a soccer ball. So there's this idea of labeling. Actually, if you Google graph labeling, you get all this math stuff about like how you put numbers on I guess vertices and edges. But we're not really interested in that. We're interested in what's referred to as the property graph. So if you're going to Google ideas about graph labeling and you're thinking about things like Neo, you want to Google a property graph. And then basically this is sort of the usual. We're seeing more graphs, we're seeing more data, and so the graphs allow us to organize data and look at these analytic approaches using graph theory. So the math is actually becoming more and more relevant. This is actually what's known as the collaboration graph. This was drawn by a mathematician named Ronald Graham with Erdős in the center, and then Erdős collaborated with like 500 mathematicians. And mathematicians are really into their Erdős number. I think one of the Neo guys has an Erdős number of 3. So in theory, if you think about it, you could really attach any kind of data to a graph. And so the idea is you could attach it to both labels. You could attach it to both edges and vertices. This is actually what's called a weighted graph. And this is actually a very important concept in graphs and algorithms and stuff, and things like like if you were modeling like distances between cities or something like that. So weights are an important thing in terms of labeling graph. It's a labeling of edges. I think technically you have weights on vertices as well. And in theory, you can actually have them on both. This is a finite state automata example where you've got your states, which are the vertices, and you've got your transitions, which are the edges. And there's many examples of this. So in Neo, you've actually got a couple of different data types that you can apply to vertices and edges, and we'll look at them. And actually, I guess if I was speaking in the Neo nomenclature, it would be nodes and relationships, which we'll see in a sec. So you've got, basically it's the Java types. You've got integers, longs, and doubles in terms of the data elements that you can do, and you've got booleans and strings. And then you've got arrays that will be homogeneous of the above types. So you can have an array of strings, but you can't have numbers in there. So essentially in the basically in the Neo nomenclature, a node is a vertex, and you can have this idea of labels on vertices, or nodes rather. And the labels are these sort of atomic ideas of, they're sort of these lexical units. So you have like person. So it's a way to sort of partition out things that you're going to have in your graph. So you could have persons and people, or person and restaurants, for example, or restaurant. And then you can attach data to it. So you could have person, and then you could put their address in it, or age or whatnot, social security number, things like that. So, and Neo allows multiple properties to be attached to nodes, as well as multiple labels. And then your properties are going to conform to the Neo data types. And then edges are called relationships. You can have what's called a type, which is similar idea to a label. And a type is, again, a lexical unit that you can query. So you could have person, friend, or person like restaurant, that kind of stuff. And then again, properties. I think you can have multiple properties applied to, you can have multiple properties applied to relationships, or you can break them out. So anyway, some thoughts about sort of. Oh, sure.
And third bullet point.
Okay.
Last sort of sentence fragment. Can be queried exactly, no question. Is that, is that clear, more clearly says it must be queried exactly? No partial matching allowed?
I think probably, right. You can't query partial on a label or a type.
I mean,
right?
you can pull them all back and then look at them. And
But you can't, like through Cypher, say like, give me PER star or something like
Yeah.
that for the type.
no, but you could say, give me all the relationship types, and then
Right.
say where it starts with something like that.
Right. So okay. So so I guess you can do that. All right. So I guess 10 is
It's
right.
not efficient comparatively.
But yeah, I guess technically, if you're explicitly querying them, you can't do that, but you can work on them once you get them.
Yeah.
Okay. Good question. If I had T-shirts, I'd throw you one. So we should get
The
those.
last one I got was too small.
Okay. All right. well, forget the T-shirt then. All right. So.
Ask a bigger question.
Yeah, your question. Your question wasn't big enough. So anyway, relationships are direct. So anyway, so I guess you can think about some of these ideas in terms of graph theory and how you're modeling your data. Your relationships are directed; they're directed edges, and so this sort of couples your modeling, I think, a little bit with how your queries. I mean, I think there's some impacts there, right, Wes? That's accurate, and then. The other thing too is that your nodes are going to have this, probably going to have like this multi-relational, multi-graph structure. So you might actually have data, you might have nodes where you actually have a lot of different relationships on them, or a lot of properties. And I think there's actually some issues with attaching multiple properties and how the indexes get built. Is that true? Actually, I think we confirmed all this, right? Now I'm feeling like we didn't confirm this. So.
The indexes are separate from how the properties connect to the nodes, but yeah.
Oh, really? Okay, all right. So, but I mean, it's also, I guess you can think about it differently that way too. And then also your data is going to potentially fall into subgraphs or subdomains, which you're tagging with labels and types across the edges and vertices. And we'll look a little bit more about subgraphs in a minute. All right. Well, this is a break point here, so we can take a break. And anyone
Can I
who's
ask you a question?
you certainly may.
You flew past the concept of partition, which has vertices in it that don't have edges connecting each other.
I can fly back to it. Okay. Yeah. Okay.
They don't have connections going to each other, but they can connect across to the other partition.
Right.
And my question is there some construct in a graph data? I mean, can you extend that into Neo in some way? Can you do?
Yeah, I mean, that's kind of like a label.
Yeah, I mean, you could have different label sets, right?
Yeah, I mean, it ends up looking like that a lot of times. Like, this might be people and this might be products they buy or something.
Okay.